Okay, so the topic of the day is, this is a small one, not a big deal, and this kind of wraps up chapter 7, is torque. Okay, so now maybe you get where we're coming from, right? So torque. So when you buy a truck, there's probably two numbers you want to look at when you're evaluating the engine on your truck. What are they?
Horsepower.
Horsepower and torque. Good. Okay, so today we're going to talk about torque. Later on, we'll talk about horsepower. But they're both important. But what is you guys probably have an idea about this. When you're talking about the torque rating on a truck, you're probably evaluating how good your truck is going to be at doing what? Towing stuff, right? Okay, good. And that's going to make sense today. You may not really, I'm sure you don't probably understand exactly what all that means, but today you will. So when we talk about physics, we could divide up into two different sections if we wanted to. And the cool thing about it is they're exactly parallel to each other. All the same stuff works in one section that works in another section. And I talked about this a little bit earlier. We don't do, kind of in a first year algebra-based physics class, we don't do a lot of rotational stuff. But rotational physics is a thing. I mean, it's an important thing. If you think about how objects can move, they can move translationally from point A to point B, right? And there are, in our universe, there are three orthogonal directions you can move things in, right? Like, let's just say, if we're focusing on this point on the front of the board up here, this point right here, then, well, one thing you could do relative to that point is you could move back and forth along this line. We'll call that the x direction, right? We could move back and forth along this axis, and we'll call that the y direction. And then we could move out of the board, straight out of the board, and call that the z axis. We have three extended dimensions in our universe, and so there's room for three independent translational motions that are independent of each other, right? Okay, we can also do rotational stuff. We could twist an object around the x-axis, we could twist it around the y-axis, or we could twist it around the z-axis, and all three of those things can happen independently. And when they all happen at the same time, it looks kind of complicated. But imagine if you've got imagine, what do you know? Okay, I just happen to have this. And I really didn't plan this. But if I'm in outer space and I twist this thing like this, it's just gonna do that, right? No big deal. Okay, it's rotating about the x-axis. At the same time, though, what if I do this? What if I push it this way? So now it's twisting this way and rotating about the z-axis, right? Two independent rotations. And then if I could even do this, right now I could even say, okay, well now let's push it that way. So now it's going to be doing something more complicated, right? You get the idea? And so you can imagine if you think about something in space, you could give it some weird twists and it would just keep twisting, right? But all three of those things would be independent, right? Just like we have these independent rotational motions. So we could, if we wanted to, when we start to compile eventually like a list of all, well, let's just do this. I'll just show you some equivalents right now. So this is going to be linear land, and that's Anglemania. Okay, so if we talk about, like, let's just look at some kinematic quantities in linear land. We know some stuff, right? We know we can talk about, for example, x being, or we call it equals position, right? Does that make sense? We've talked about this stuff. V is velocity, A is acceleration. Well, we have corresponding things in Anglemania. Corresponding to position is angular position. Okay, so for example, if this is the center and this object right here is revolving around that center, then if it starts right here and it ends right there, well then that's theta. That's its angular position. Okay, make sense? So how far has it rotated? Velocity is replaced by, V is replaced by omega. Angular velocity, well, what do you suppose that's measuring? Velocity is measuring how much the position is changing with time. What do you suppose angular velocity is measuring? Well, essentially, how fast is it spinning around the object? How fast is the angular position changing, right? And we're not going to spend a lot of time with this stuff. The point is not that I'm going to throw a bunch of really complicated formulas at you, angular physics formulas. We'll come back and look at some of this stuff. But the thing I want you to appreciate here is that we could, and it wouldn't be that big a deal, because there's something really cool that happens. And then alpha is, for example, angular acceleration. Okay, those are all exactly equivalent. We've got, for example, let's take this guy right there, kinematic equation number 1. What's really cool about this, you're getting a bunch of physics for free here that you already know, is that I could take kinematics equation number 1, delta D equals average velocity times t, and what's that going to become in Angulvania? Yeah, angular displacement, change in theta, equals average angular velocity times time. What do you know? They're exactly the same. All of those would be, in fact. Everything you do in linear land has an exact parallel in Angulvania, which is really cool. So all the physics you've learned, I could give you parallel problem sets to all those right now in Angulvania, and you could do them. They'd be a little weird because we're not used to. We think more in terms of, of displacements. It's just the way. How often do you really do a lot of rotational stuff in your life? You don't do a ton of it, right? You drive home. You mostly are walking from point A to point B, throwing the ball over there. You don't really oftentimes think about the rotational part, but it's there. There's some other things too. So we could easily write down all 4 of those those linear land kinematics problems just by substituting the equivalent variables. We could turn all those into Angulvania kinematics equations, right? There's some other stuff too, though. What are some other quantities we've talked about? Really, there's not much at this point. What's the other big quantity we've talked about? Force, right? We haven't really talked about much else. We're just on the cusp of talking about some other things. We're going to be talking very shortly about momentum and about energy and things like that. So we'll add some other quantities that we'll understand. But for now, we spent a lot of time on force because force is a big deal, right? Force is really important. Plays a big role in physics. Dynamics and statics are all about forces. So what do you think the Angulvania equivalent of force is? It is torque. It is torque. Torque, and that's a good way to think about it. Torque is literally it's like a twisting force. That's what torque is, okay? So we're going to come up with some relationships with torque, and we don't do a lot with it, but what I think we'll do is we'll kind of wrap up this book. We'll sort of go through this book and go through mechanics, and then we'll maybe go back and take a look at, okay, so what if we filled in a couple things with a little bit of extra angular physics? Because there is some pretty cool stuff that we can talk about that's not that excessively complicated. And then we'll just kind of bail on mechanics, and we'll go do a fairly non-mathematical survey of other kinds of physics. For the math will get easier. Talk about, optics, and talk about waves, and we'll talk about thermodynamics and just fun stuff like that. Yeah.
So for the sign of torque, is that basically just half pi?
These are all, okay, yeah, you notice that's a tau. You notice that all of the angular variables are these weird Greek symbols. Yeah, they're just the Greek equivalent. So this is a Greek A, that's a Greek V, that's not really theta is just what we use for an angle. But and that's not really an F, I don't think. I think a tau is a T. But for whatever reason, we call it torque and we name it a T. Okay? But it's a weird Greek T.
So if I draw it better, it looks kind of like,
It's like half a pie.
yeah, I mean, kind of. Oops. It looks like, I'll show you what it's supposed to look like.
Master of physics, not master of
No, not master of drawing by any stretch of the imagination. Where do I go? Tau.
trustworthy.
There, well, I mean, that's one way to draw it. It just looks like a T. Usually you see it a little differently than that.
Well, there was the little one.
Yeah, yeah,
Yeah, it's like half a pie.
yeah.
Hey, just go to images, go back.
Oh, there we go. Yeah, good idea.
I was gonna say, I thought you were gonna find something other than
Yeah, yeah. That's probably not safe to do. I probably shouldn't be just like Googling things.
Greek symbol tau or something.
Yeah, there we go.
Just see what happens.
No, I'll preview them here.
Come on. Nothing gets through the school's filtration
Uh-huh,
system.
right. Well, none of these look great to me, honestly. But okay, so this is kind of that one's kind of it. Sort of. Anyway, when I make that weird scribble, it looks like I'm having some kind of a seizure up here. That's what I'm doing. I'm drawing a towel. Okay, so. All right, so let's talk about that. What's torque? So here's the way torque works. Now, you already know some stuff about torque. If you want to, let's say you want to turn a bolt, a stubborn, rusted bolt, and it's hard to turn, what are you going to do? What's your strategy? What are you going to do?
You're gonna like put a pipe over the handle.
Okay, one thing you could do on your wrench is you could put a pipe over the handle. Why?
Cause it's left towards.
Okay, because it makes the handle longer, and it's leverage in a way. That's a good way to think about it. Okay, so here's the picture we can draw then. If we want to turn this bolt, it's hex head, right? So aren't they hex, like a bolt would have 6 heads, right?
Yeah.
So there's the bolt, and let's say, I can really tricky this actually. Oh, this is an excuse to play with my toys. I'll go like this. Watch this. So there's the bolt. Pretty good, huh? How do you think about that? That's an impressive bolt, I agree. Okay, so there's my bolt, and here's my wrench. So my wrench just kind of looks like. That's not a great wrench, but you get the idea. Right, there's my wrench. Okay, so I want to twist this bolt, right? One thing I want to do is I want to get a longer wrench if I want to have more torque. Okay, there's something else that we just automatically do. It would just make sense.
Much stronger.
In what direction, if I want to loosen this bolt, in what direction should I apply force to the handle?
Left or right?
Okay, but like, would it make any difference, for example, if I pushed it in that direction?
Oh,
Or
push it
in-
perpendicular.
Okay, I want to push it perpendicular. Yes, I do. That's going to make a big difference. I want to push perpendicular because here's how we define torque. Torque is defined as, I'm going to call, this is the length of the lever. The lever extends from the center of the axis of twisting, right? So the center of the bolt. It's going to go from there out to wherever I apply the force, right? So that's what we're going to call R. Okay, that's going to be the length of the lever, okay? But torque is not defined by the length of the lever, but by the length of the lever arm, which is the distance between the line of force and where the center of the bolt is, right? So if I push in this direction right here, for example, then the lever arm is only going to be that long, okay? Because the line of force gets closer to the center of the bolt than the end of the wrench, right? And so if that's the case, obviously, in what direction do I want to push? Well, I want to push perpendicular to the wrench, right? Because then the line of force is going to extend the entire length of the lever, right? And so the lever arm ends up being as long as the lever, right? Okay, does that make sense? So we call the angle between the line of force and the lever, we call that theta, right? So then what's the component? If this is my, let's say this is my force vector, right? I could break that force vector up into components. I could break it up into a component that's parallel to the wrench that does nothing, and a component that's perpendicular to the wrench, which does do something. If this is F, what's, in terms of theta, what's going to be the normal component, the perpendicular component of the force that actually contributes to the torque? What's it going to be? It's going to be sine, isn't it? Because it's an opposite issue. So then this component right here is going to be F sine theta. Agree? So that's the part that contributes the force, right? And then if I do that, if I break the force up into components, then I get to take that component and have it multiplied by the entire lever arm. Agreed? So my formula ends up just being that torque equals F sine theta times R. Okay? Make sense? There's another way I could look at this though, isn't there? I can also look at this as, okay, I'm going to use the whole force, but I'm going to multiply the whole force by only that lever arm, right? Does that make sense? So if that's theta, right? If that's theta, then what fraction of the entire lever, because that's also a right angle, what fraction of the entire lever is equivalent to, or what, yeah. So then, now the triangle we've got, let me just grab that triangle again. So here's the triangle, right? The triangle looks like this. Here's my line of force. Right, we call that the line of force, by the way. The line along which the force is acting.
Why is that line straight, not like arc?
What do you mean?
Like if it's radial force, why is the?
Well, if you push on
Are you just
something-
talking about so?
Which
You know what
line?
I'm saying? Like if you're
That
applying
one?
force to, no, your line of force.
Oh, the line of force. Yeah, okay, because we're not actually, we're just saying, this is the force I'm going to apply to the
Just wants.
wrench to make it turn. And then the effect is going to be, it's going to twist the bolt that way, right? If this is the line of force, right, and this is R, then we said that this is the perpendicular distance right there is L, so that's the lever arm, right? Well, if this is theta, then what's L in terms of R? Because that's a right angle. So that's the hypotenuse, right? So what's that going to be? It's going to be a sine issue again, isn't it? Right? That component's going to be R sine theta, right? So there's another way we can look at this. And they're completely equivalent is what I want to show you. So we could also write the torque equation as the whole force times the lever arm, which is R sine theta. Right? So which one is it? Oh, it doesn't matter. Either one. They both work. In fact, I really could just, I don't even have to put the parentheses in there, do I? I really could just write this as, whoops, I could just write this as torque equals F R sine theta. And when you go a little further in math, one thing you'll talk about is some other weird kinds of vector products, and this is what's called a vector cross product. we can just cross the force and the radius vectors, and it's equal to that. But I won't get into that stuff now.
Is it possible to have a truly curved force?
No, you can't. The force has a direction. It's always right. Force is always going to be linear. Okay, so then probably the way that's going to be the easiest for you guys to think of, or not the easiest, the way that's going to make the most sense is going to be that way. And it kind of makes sense that way because you're pushing with a certain force, call it F, on the wrench, right? And what's changing is the direction in which you push it changes the length of the effective lever arm. And so let's just say as a group that this is the way we're going to think about it, even though any of those would be fine, right? We could either think about it as the full force times the lever arm, or we could think about it as only the perpendicular component of force times the length of the whole lever. But this is the one that probably makes the most sense to use. And it's consistent with our book. Okay? Make sense? Okay? So then, let's explore something here. You know, this is overkill. You guys saw this stuff pretty darn easily.
Just
But
to confirm, those parentheses are redundant, right?
they are.
Okay.
Yeah, but the reason we write it this way is just that this really becomes torque equals force times lever arm, right? Where lever arm is just the perpendicular distance between the axis of rotation and the line of force. Yeah. Okay. All right, so let's see, I want to show you one thing here. Let's go this one. Okay, so then okay, so what I've done here, I've just taken an example of what if we've got a half-meter long wrench, right? And we're going to calculate the torque. So then we've got the equation, the torque equals force times lever arm, right? Okay, so the force is, let's just say that the force is going to be X. Okay, the lever arm is going to be, so we get X in this case. Well, I better write it in terms of stuff that makes sense to us. So force times R sine theta, but R is going to be 0.5. And because I can't just define the variables at Desmos, I have to call this one X and this one Y, right? So the torque is going to be replaced by a Y, and the force is going to become X, and the R becomes 0.5 sine theta, and the theta I had to call an A, just because Desmos doesn't let me call it. If I call it a theta, it assumes it's a variable and I can't use a slider. But now look what happens here. So if I'm going to set the force at, let's just say 100. So let's just say we're going to use 100 newtons, or we could be talking about pounds if we wanted. But the standard units of torque would probably be in terms of what? If it's going to be in terms of torque is, we said, it's going to be force times lever arm. So what's the standard unit of force for us? Newtons, right? What's the standard unit of distance? Meters. So the standard SI unit for torque is going to be a Newton meter, right? Now you could use other weird units, and we often do. What's another unit of force? If you're buying a truck, they don't use Newton meters. What do they use? Foot pounds, right? So the pounds are the force part, and the distance is the foot part, right? But still, it's a product of force times distance, so it still works, just a weird unit, right? Okay. So then I'm going to control here's the length of here's the amount of force that's being applied. We'll just call it 100, whatever. We'll make this foot pounds if we want to. So that's going to be measured in 100 pounds. And the length of the lever, I guess, is going to be half a foot. So it's going to be 6 inches, let's say. Okay. So then we want to know by controlling, sliding the angle, what angle is going to give us the most bang for our buck? What's gonna give us, this is the torque graph, right, in terms of X and A. If I slide the angle, look what happens, it gets bigger and then it gets smaller again. Right, so the intersection, if we wanna know how much torque are we getting when we push with 100 pounds of force, it's gonna be how high is the red function when it crosses X equals 100. Where is it a maximum, predictably? You should be able to tell me, where's it gonna be a maximum? You already told me this. At what angle are we gonna get the most torque for our force? No, it was, remember, this is theta, right? So what's it gonna be? It's 90, yeah, right? So there's the, right, if this is the center of the rotation, and this is R, and we're applying our force, right? So here's the line of force, then that's theta, and you guys all told me you want to push perpendicularly, right? So theta should be at a right angle. Well, we can see that on here, right? You can see that at 90, that's where that thing is at its highest point, isn't it? Right there at 90. Okay, yep.
So, would this, like, if this was a physics calculus class, would this relate to optimization?
It certainly could, yeah, we could, right, I mean, if we were doing calculus-based, then we could actually look at this and say, well, let's maximize, let's find the angle that's gonna maximize the torque, and if we did that, we'd find it's 90 degrees.
Right.
Okay, you can kind of see that on here, though, and it's
Yeah.
not even linear, is it? If I slide this thing at constant speed, look what that thing does. Isn't then interesting how it goes fast, and then it slows down, and then it goes fast again, right? So, you don't have to push it exactly 90 to get almost all of the effective torque out of this. But if you push at a bad angle, like 25 or 30, you're not getting very much torque, right? Okay. All right, so that makes sense. You can, those problems are a piece of cake, right? You're just gonna, all I'm gonna have you do, here, I'll give you an example. Just do this real quick. Problem set's real simple. This is all only kind of stuff I want you to do. All right, stuff like this.
Oh, no, I just, the log. I'm taking notes on what sound it makes when you type in your password, so I can check to see which buttons make.
Oh, okay, gotcha. Okay, that's good to know.
Best way to do it.
Okay, that is recorded too. It's going to be admissible in a court of law, just so you know.
Okay,
Okay, so
wasn't that a funny joke?
yeah. So the maximum torque that can be exerted on a bolt using a 0.704 meter long wrench and 216 newtons of pushing force is what? How am I going to figure it out?
Just plug it in.
So if this is the length of the wrench and that's the pushing force, what's the most torque I could get? How would I find it? That times that, right? Because if I push at a 90-degree angle, if I push perpendicular to the lever, then the lever arm uses the whole wrench, right?
Yep.
Make sense? Everybody see that? So in a picture, if I make this angle 90 instead, right? So right now, tell me if I don't need to do it, if it is overkill. But this is, so there's the lever arm, but if I push at this angle, so that's my force instead, then that's the lever arm, right? It's equal to R, it's equal to the whole wrench. Okay? So there's one. I just multiply those together, no biggie. What about something like this? How about that one? So now it's telling me I'm using a .472 meter long wrench, 180 newtons of pushing force applied at a specific angle. What am I gonna do? What's the formula gonna be there?
Yeah, it's just be a
Sine.
force
Yeah.
applied by the sine.
Yeah, good. So it's gonna be 180 newtons times .472 sine 73.3, right? Okay. All right. What about with truck? Now let's talk trucks.
Truck.
Let's talk trucks. Okay. So if we want to buy a truck that we're going to be able to pull a big trailer with, right? So pull a boat. There you go. So then we want lots of torque. Well, how does that work? Where is the torque being exerted? Okay, so when we think of it this way, when we twist the axle on a car, the axle is converted into a twisting force or in the drive shaft, it's converted into a twisting force to the axle, right? So we're going to twist that axle. How much twisting force is applied is telling you how much torque the truck has. What does that translate into in terms of your ability to tow something?
More torque.
Okay, more torque the bigger the boat, but really think about this in terms of the stuff we've already talked about earlier in the year, in terms of Newton's third law, right? If we want to push forward with our truck, that means that essentially what is the truck pushing on when it drives forward?
The ground.
It's pushing on the road, isn't it? In what direction is the truck pushing the road? It's pushing the road that way. And so if we call that the action force, truck pushes on road, what's the reaction force? The road pushes on the truck in that direction, right? So really what makes the truck go forward and pull the load is the amount of force that it can exert on the ground, right? Okay, so how is that related to the torque? Well, think about this now. If we have a wheel instead of a wrench or instead of a lever, a wheel is effectively the same thing, right? Oops. So there's our road, and here's our tire. Okay, so there's our tire, right? Okay, here's going to be the center. Here's the center of the tire, right? And the force is being applied right there, isn't it? Right? In what direction is the tire applying a force?
Oh, that's where they have.
That direction, right? Okay, that make sense? Okay, so this really is L, isn't it? Right? See, we could think about this, just imagine the spokes on the tire, right? Every time the tire rolls a little bit, there's still going to be a spoke that's connecting it to the ground, right? Because the only point that the tire touches is right there, right? Make sense? So a tire is just like a continuous lever. It rolls forward, that's all right. There's just a new lever connecting the center of the tire to the ground, okay? And so we know that if that's L and that's F, well, this is pretty simple then, right? The torque is just going to be the driving force times the radius of the tire. That's all the effective lever arm is, right? Does that make sense? So if you really want to be able to pull a lot of stuff, what kind of tires do you probably want to buy for your truck? Big ones?
Yes.
Wrong.
Little ones.
You want to buy little ones.
Because people don't tow a lot of stuff with like 37s on, but they tow a lot with like 33s on.
And there's a reason for that. Because if we solve this for F, right, because we're trying to identify F, right? F is the important part of this. That's the force that's applied to the road by the truck, which means that's how hard the road is pushing back on the truck, right? If I want to pull a big cattle trailer up a hill, that's heavy, right? I got to be able to apply a lot of force to the road because it's got to be able to push back with a lot of force to get me up the hill, right? Make sense? So if I solve for F, what do I have to do to both sides?
Oh, because the torque is constant, so that makes sense.
Right? See what I'm saying? There's a maximum torque that the engine can output. It's just, there just is. I mean, every engine's gonna be limited. So for a fixed amount of torque that our engine's providing, look at that. The radius of the tire is the effective lever arm. That's on the bottom of the fraction. So by making the radius smaller, I make the overall force that's being applied bigger, right? And we can see that. What do you know? I just happen to have made another little, cool little. I'm kind of liking this whole Desmos thing. So if I go, there we go, right there. So let's look at this one then. What this is graphing is, we're just assuming here, I just made up a number. So let's just say that we've got 7,538 Newton meters of torque available, right? And let's just say hypothetically that our radius is, well, that's a pretty big radius. Let's say our radius, I'm gonna change this a little bit. So the radius is going to vary between 0 and 1. How about? Okay, so if is that even doing anything? Oh, no, it's not. It's not doing anything. That's right. Anyway, that's not going to do anything. It doesn't matter. It's not going to do anything. But look here. I don't need it to, because look at these points on the graph. These are measuring, X is my radius, right? And Y is force, right? Because remember, this is just, we have the equation. Force just equals torque divided by lever arm, right? So force is Y. That's my constant torque that my truck can provide. And I'm going to experiment, see what happens when I change the radius of my tires, right? Well, this is what happens. If I make my tire have a radius of 0.8 meters, that's a pretty big tire. That's a huge tire. It'd be 1.5 meters across, so that's pretty big. My torque, or the force I can apply is only 9,422.5 newtons, right? I don't know if that's realistic or not, but if we make this a lot smaller, if we go back, for example, to something like, let's make it about 0.2 of a meter. So then it'd be 40 centimeters across the whole tire. That's not very big. It's a pretty small tire, but look at all the extra force we get out of that. We get almost 38,000 newtons compared to, where were we before? 0.8.
Can you find like points that would be referenceable to that?
Yeah, we could. I mean, let's change the numbers. What's the torque on a? We'll do this in terms of feet and.
We have it 800 foot-pounds.
800 foot-pounds. Okay, so let's change it. Let's try this. So if we do 800 foot-pounds of torque, and then what would be? We'll do this in terms of feet. How about? So what would be a reasonable? Like, what's an average radius of a tire? I'm talking about for the radius, not the diameter. So like what would be, what's the full diameter of a big tire? Like 32 inches? That'd be huge, wouldn't it?
Yeah, 35s are like large average.
Okay, so we'll say 36 is pretty big. That's easy. Then that's 1.5 feet would be the radius, right? So then here's what the. So there's what you'd get. Then at 1.5 feet, you'd get about 533 pounds of force pushing the truck forward. Okay, but now compare that to, right, if we went down to a smaller tire, let's say we go down to a tire that's only 24 inches in diameter.
So with a tire that big, you'd be putting 800 foot-pounds into it, but you'd only be getting 533 foot-pounds back.
That's right. You don't, no, pounds, because that's how much force is pushing it forward, right? Okay, so if you had a big trailer, you couldn't, without those big of tires, you'd have a hard time, you'd have a pretty hard time going up a steep hill.
Getting up that hill to the reservoir.
But if we take it down, let's just take it down to like 0.9. Now that moves it up quite a bit. Now you're up to 890, right? And if you go down even smaller, I mean, this is getting kind of ridiculous, but if you went down to something like, let's just say you went down to, if you had 8-inch tires on there, you've multiplied that up to 4,000, right? Okay, so it gets a lot bigger. Now, what's the obvious disadvantage? If you put really small tires in,
You're not gonna be able to go as fast.
yeah, you can't, right, you're not gonna be able to go nearly as fast, but you get the idea. I mean, the smaller the tires, the more you're gonna be able to use the torque in your engine. Now, what's the other thing you could do, though?
Change ratios.
Okay, you could change the gear ratios too, couldn't you? Right, you could change the gear ratios so that you could effectively change the amount of torque that the engine's providing to the axle, right? Yeah. Mm-hmm. There's going to be some fundamental limit there, though, because at some point, like, you could never put on 6-foot tires on a truck axle, because at some point you're going to have to twist that truck axle so hard that it's going to literally break the axle. Right. You'd have to have a great big.
I don't know, Mr. Roy. I was down in Burns visiting my grandparents this one time, and this guy literally had like tires that close to as tall as me.
Upgraded tires.
Well, you could do stuff like that, but if you didn't make some really substantial changes to the truck, it's not going to work, because at some point, it's just metal. I mean, metal at some point is going to break.
What about my little bulldog? Like,
All right, so now you know about. So now, when we get into the next chapter, we'll be able to come back and revisit this conversation and talk about horsepower. Because horsepower is also important. Yeah.
Are we gonna be taking tests over this?
Yeah, we will. We will.
how many
I wish,
horses
yes,
are-
you probably want time to wrap this stuff up, I'm sure. And the torque one, there's only gonna be like 4 or 5 problems on it. It won't be a big deal. That's really not a huge part of the chapter. Mostly it's gonna be the other stuff.
So it's overnight.
Yes, got a full workday tomorrow. I got Chromebooks, get questions answered, et cetera, et cetera. Okay, hey,